morning, students. In today's class, we shall study something about the exponential function. So to understand the exponential function, we are going to take number of examples. So let us take here an example like equation y is equal to x. Let's take y is equal to x square, y is equal to x cube, y is equal to x to the power 4, and let us draw graphs of these functions. And to draw graphs, I'll draw graphs only in the first quadrant. Alright, so x has to be greater than or equal to 0. So when we take x is equal to 0, y will be 0. So all these equations will have a curve passing through the origin. Alright, let's start for the first one. So here I'll write down here that when x is 1, y is 1, when x is 2, y is 2. So that means this is going to be a straight line and it goes like this. So this is the graph of the equation y is equal to x. Let's move down to this one. Here again I'll write down just two values. When x is 1, y is 1. When x is 2, y is 4. So here this is going to be, you must have identified that this is basically equation of a parabola with focus on the positive y-axis. So since we are drawing the curves only in the first quadrant, so the parabola, a part of the parabola would be somewhat like this. Alright, this is the curve of y is equal to x square. Moving down to the third one, here again, if x is 1, y is 1, if x is 2, y is 8. So the curve would be somewhat like this. Here this is the curve of y is equal to x cube. And likewise when we draw the curve of this, when x is 2, y is 16, so it will be steeper than this. So I am basically drawing here three curves only. So for these three curves you see as the power of x is increasing, the slope of these curves is also increasing. More the power, the steeper is the curve. So what we have dealt with is not the exponential function but polynomial equations. The four equations that I have written here are basically polynomial equations. All these equations have a common factor. First, each of these equations passes through origin. All the equations pass through the point 1, 1, and then as the value of x increases, goes beyond 1, the slope or the curve gets more steeper. So as I said, none of these is an exponential function. So what we are trying to see here is basically the steepness of the curve right now. As the power of x increases, the curve becomes steeper. So we are looking for a function which is still steeper than all these functions. So let us explore a function of this kind. Y is equal to 10 to the power x. First, let us compare this equation with all these four equations. Notice left side is the variable y. On the right side, you have a base which is a constant. Alright, it is not a polynomial equation like this. So this kind of a function where the base is a constant and it is raised to a variable, this is known as the exponential function. Here, if x is 1, y is 10. Unlike in these cases, x is 1, y is also 1. Right? If x is 2, then you can see y is 100. When x is 2, y is 100. That is the maximum change taking place. Look at all these values of y when x is 2. Alright. Value of y 2, 4, 8, 16, and now we are getting the value 100. So that means a function which shows such a big increment in y variable is said to be an exponential function. So the graph of the exponential function, okay, let's see, when x is 0 here, y is 1, so that point is here with coordinates 0, 1, and if you plot these points, you will obtain that the curve is somewhat like this. Alright, you can see here according to the graph also the steepness of this curve. Okay, so the exponential function is one function which gives us the maximum steep or the maximum slope at any point of the curve. Alright, so here is what we come to know about the exponential function. So now let us write down the basic definition of an exponential function. So the basic definition is a function y equal to fx, which is defined as b is equal to x, is called the exponential function if certain conditions satisfy. What is that? The first condition, the base b is greater than 1. Second condition, b to the power x is greater than 0, which also means that y is greater than 0. Alright, and then if you look at this graph, this is graph of an increasing function. So the third condition it has to satisfy is that we obtain the graph of an increasing function. So there are three conditions here. So I'll rewrite this equation here. Y is equal to b to the power x. This is in standard form called the exponential function. What is special about exponential function? The base is greater than 1. B to the power x always has to be greater than 0, hence y will also be greater than 0, and the increasing function graph is obtained. What is an increasing function? Let's see that. Come to this graph over here. Look at any of these graphs. When you start moving from the extreme left of the graph towards the right, as you keep moving, you see that the graph is moving upwards. If the graph is moving upwards while you're moving from left towards right, that means this is graph of an increasing function. Alright, any of these curves also you pick up, suppose we pick up this one, when you move from left to right this way, you see that the graph is or the curve is moving upwards. So each of these is an increasing function. So now since we have defined here y is equal to bx, let's draw the graph for this function only and then see what important things can be derived from the graph. So here when x is 0, y will be equal to 1. So that point x is 0, y is 1 is this. So the curve will pass through the point 0, 1. As you put in various values of x, you get corresponding values of y. Once you decide what is the base is any real number greater than 1. So the moment you draw a graph of this kind is obtained like this. Looking at this graph, we can see number of things. The first point that comes into our mind is the domain of the exponential function. What is the domain? Domain basically means the values that you can assign to x. You can see here along the x-axis, if you move, it can be any negative value of x, it can be 0, it can be any positive value of x. That means the domain is the set of real numbers. Next, what is the range? Range means values of y. We have already stated here y is greater than 0. As you can see, the curve lies in the first and second quadrant. So that means y is greater than 0. So what is the range? The range is 0 to infinity. The third point you also notice here that this is graph of an increasing function, which I have just explained. Okay, graph of increasing function. every exponential function will pass through the point 0, 1. So the graph or the curve will always pass through the point 0, 1. And then you also see, as you move towards larger negative values of x, you will see that this curve comes closer and closer to the x-axis but does not touch it. So that means y cannot be 0. Y can tend to 0. You can see here, you can come closer and closer to the x-axis, but then the curve will never intersect the x-axis, because if it intersects the x-axis, y becomes equal to 0. Alright, so the curve will never intersect the x-axis. So once again, let us see what is basically an exponential function. A function of this kind, a constant raised to a variable. This is a constant function, an exponential function. The graph is like this. Important points: the graph of exponential function will always pass through 0, 1. Domain is real numbers. This is the range. It is graph of an increasing function. The graph will always pass through this point, and y cannot be 0. That means y can never intersect the x-axis. Let's move ahead now. Let's see, looking at this basic definition, one question that usually comes into our mind is that why is the base always greater than 1? So let's explore the base. First, it is greater than 1. If you take any real value which is greater than 1, whether it is 2, 100 or any other real number like 3.5, the curve will obtain would be like this only. Alright. Let us explore various cases. Suppose b is equal to 1. So the first situation that we are going to explore here is b is equal to 1. If b is equal to 1, then the exponential function becomes 1 raised to power x. Now here you assign different values to x, whether x is 0, x is 1, x is 2. You will notice that the value of y turns out to be always 1. Alright, so something, now if we draw the graph here, the graph would be for any value of x, alright, y is going to be greater than 1. So y is going to be equal to 1. So this is the point, and this kind of a line would be obtained. What is this point? This point is 0, 1. X is 0, y is 1. Alright, this is the curve obtained. Look at this curve and compare it from here. The domain of, according to the graph, the domain of this function is the set of real numbers. What is its range? Its range means values of y. Are values of y lying in this range? No, value of y is exactly 1. So this condition is not satisfied. Is this graph of increasing function? Is this graph of increasing function? Obviously not. As x is increasing, y is not increasing. Y remains 1 only. So this is not graph of increasing function. So you can see a second condition, third condition, not satisfied. Fourth condition, the graph is passing through the point 0, 1, y is not 0. So when these two conditions are not satisfied, so in that case we don't consider the function to be an exponential function. Hence it is clear that b cannot be equal to 1. Okay, if b is not 1, second situation, can b be equal to 0? If b is equal to 0, let's see then. The function is y is equal to 0 to the power x. Alright, so here let's again see x is 0, 1, 2, what is y? When x is 0, y is 0 upon 0. This is something which is not defined. Alright, when x is 1, y is 0. When x is 2, y is 0. For any other value of x, y will be 0. What we note here, the graph. Let's see. When x is 0, is the graph passing through 1? Obviously not, as is required. One important requisite of the exponential graph is it has to pass through 0, 1. But when x is 0, y is not defined. So that point, this point is not satisfied. When x is 1, y is 0. X is 1, y is 0, x is 2, y is 0. So leaving out this point, okay, this is the graph of the function obtained. This graph, this curve or the line does not have domain R. Alright, you can see here negative values of x are not lying here. The range is only 0, that too not at x is equal to 0. This is not graph of increasing function, it's a straight line parallel to x-axis, so it is not graph of increasing function. This condition we have already seen. Y is not 0, here y is coming out to be equal to 0. So since many of these conditions are not satisfied, so once again we can say that b cannot be equal to 0, because if b is equal to 0, these conditions for a function to be an exponential function are not satisfied. Let's move on to the third situation now. Third situation, b is something between 0 and 1. It cannot be 0, it cannot be 1. So let us take, suppose b is equal to half. So in that case, the exponential function would become y is equal to half to the power x. Alright, now let's plot some points. X is 0, so y will be equal to 1. X is 1, y is half. X is 2, y is 1/4. And you can similarly find out some more points, and then plotting the graph. The point 0, 1 is on the curve. So here is the point 0, 1. Now you can see here that values of x are increasing from 0, 1, 2, 3, 4 and so on. What is happening to values of y? Decreasing. This is 1, here is 0.5, the next value is 0.25, so value of y is decreasing. So that means when we plot the curve, it would be a curve like this. Alright, this curve and the curve over there do not look similar. There's something which is same. The first point, both the curves have got a point 0, 1 on it. Secondly, look at the domain. What is the domain? All real numbers. So here also x is all real numbers. What is the range? 0 to infinity. Second condition also satisfied. Is this graph of increasing function? Let's check. Start from the extreme left and start moving along. You notice that you move down the curve. The moment you're moving down the curve, that means this is graph of a decreasing function. If it is graph of decreasing function, that means this graph basically represents decay. Any kind of decay takes place, it will happen in this manner. Any kind of growth that takes place will happen like this. Alright, so you can see it is not an increasing function. Can y be 0? It cannot be 0. So one condition not satisfied, this is not an exponential function. Or in other words, you can say that an exponential function represents growth, like population of a country increases exponentially. Alright, the compound interest given in the banks increases exponentially. So whenever there is a positive increment, we refer to it as an exponential function. Alright, but whenever the function represents a decay, like in this case, although the base is a constant, alright, raised to power variable, satisfies definition of exponential function, but finally it shows decay. Hence we do not consider it to be an exponential function, because we are referring to exponential function as a growth function. So hence we know b cannot be in the interval 0 to 1. Last situation, can b be less than 0? Negative. Let's take an example. Suppose I have taken base as -2. Let's again explore. Y is 0, sorry, x is 0, so y is 1, x is 1, y is -2, x is 2, y is 4, x is 3, y is -8 and so on. Without drawing the graph also, you can notice here two things. First of all, the curve will pass through the point 0, 1, alright, and then again see x is increasing, right? What is happening to y? Y from this point to this point it is decreasing. From -2 to -4 it is increasing. From 4 to -8 it is decreasing. That means the graph will be somewhat somewhere increasing and somewhere decreasing. It will not show us a regular pattern whether it is increasing throughout or whether it is decreasing throughout. Okay, so that is why b cannot be negative. Another reason, suppose we take the base as -2. What is x? X is any real number. Suppose we take a real number half. That means y is square root of -2, and you know this is a complex number, root 2 iota. So on the real coordinate system, can we plot x, y and this value together? It will be very difficult. Alright, so for certain values you may get, for certain values of x you may get complex values of y as well, which cannot be easily plotted. Hence b always has to be greater than 1. b cannot be 0, b cannot be 1, b cannot be lying between 0 and 1, b cannot be less than 0. What is b? Base. It is a real number. What is the restriction on this real number? Is that it has to be greater than 1. Only then we will call it an exponential function. So exponential function we are writing as y is equal to b to the power x, where we are defining that b has to be greater than 1. So there are two different cases that arise. First situation, base can be equal to 10. That's a real number, greater than 1, condition satisfied. So if it is y is equal to 10 to the power x, it is an exponential function. So whenever base is 10, we call it a common exponential function. The base can be equal to e. What is e? E is basically called Euler's number. Alright, we will study in details about Euler's number also. As of now, it is a real number greater than 1. If the base is taken to be e, our function is like this, and we call it the natural exponential function. What is special about y is equal to e to the power x? When you differentiate this function, this is the only function which gives you back the same function even after differentiation. You differentiate x square, you don't get back x square, right? You differentiate sine x with respect to x, you don't get back the same function sine x. But when you differentiate e to the power x, you get back the same function. That is why this function plays a major role in differentiation. And hence, whenever we refer to exponential function, we mean that y is equal to e to the power x. This is the standard exponential function. Alright, you make changes in x, it becomes a composite function. For example, y is equal to e to the power 2x, it can be e to the power x square, it can be e to the power 2x plus 3, something like this. So as whenever the power of the function changes, it becomes a composite function. It can also be e to the power sine x. Alright, so now we are going to see what exactly is e. So here, Euler was a Swiss mathematician who came to know what exactly is e. So we are also going to explore what is e. As of now, we know e is a real number which is greater than 1. What did Euler tell us more about e? That's what we are going to explore. Okay, so Euler said that e can be represented by this infinite series. This. So the Swiss mathematician Euler said that this real number e can be expressed as this series. So we are trying to find out what is the sum of this series, say up to n terms. Alright, up till this term. So how many terms are these? Basically n plus 1. So here let us see one thing. 1 upon 3 factorial is basically 1 upon 6. And 1 upon 2 square is 1 upon 4. So when you compare 1 by 6 and 1 by 4, you get to know that 1 by 4 is greater than 1 by 6. Okay, I have started from this term. The next term after this is 1 upon 4 factorial, and 1 upon 4 factorial is 1 by 24. We have a number like 1 by 2 cube, and this is equal to 1 by 8. And when we compare 1 by 24 and 1 by 8, we get to know that 1 by 8 is larger than 1 by 24. So I think you can make out the relation. 3 factorial, power is 2. Here it is 4 and here it is 3. So in a generalized manner, we can write down 1 upon n factorial should be less than 1 upon 2 raised to power n minus 1. 1 upon 3 factorial less than 1 upon 2 square. 1 upon 4 factorial less than 1 upon 2 cube. Similarly, 1 upon n factorial is less than 1 upon 2 raised to power n minus 1. So, let us take all these terms. Fine. Sum of all these terms, 1 upon 3 factorial plus 1 upon 4 factorial plus 1 upon 5 factorial till 1 upon n factorial. Sum of all these terms would be less than, starting from here, 1 upon 2 square plus 1 upon 2 cube till 1 upon 2 raised to power n minus 1. Okay, so I think this inequality makes sense and is easy to understand. Since we started from here, let us add these many terms on both sides of the inequality. So we are adding 1 plus 1 upon 1 factorial plus 1 upon 2 factorial. This is what we are adding on both sides. Adding to this, we get alright, left hand side. Likewise, the right hand side, what are we adding? 1 plus 1 upon 1 factorial plus 1 upon 2 factorial, and starting from here 1 upon 2 square plus 1 upon 2 cube till 1 upon 2 n minus 1. So you can see here what is this. This is this series represented by E. Of course there are more terms. I've just taken few number of terms here. Alright, and now move on to the right hand side. On the right hand side, look at this expression 1 plus. If you notice, this is an infinite GP because I have just stopped here. There are more terms that you can write down. There are some more terms here. Fine. So this is an infinite GP, and we know sum of an infinite GP. Sum of an infinite GP is given by this relation. So using this relation, A is the first term, which is 1. Denominator 1 minus R. R is half. So simplifying here, this side, we get to know that E is less than, simplifying this will give us 1 plus 2. So we get to know that E is less than 3. So this number, which is E, is less than 3. Look into this expression. The first term is 1, next term is 1, and all the other terms are less than 1. So that means it is 1 plus 1, 2 plus something. So we get to know that E is greater than 2 and less than 3. E is greater than 2 and less than 3 means, by careful experimentation, Euler had found out that the exact value of E. Now it was not possible to find the exact value of E because E is an irrational number. So to some extent, we can write down close to 2 or 3 decimal places. It was found that the value of E is 2.718 and E is an irrational number. So you can see what is this base? It is greater than 1. Alright, so this is how we find out value of E. The entire idea of doing all this work was to show that the base is greater than 1 and it is a real number. Of course, it is an irrational number, but yes, again a real number. Now, the Swiss mathematician Euler also mentioned that the exponential e to the power x can be written as this expression. like this. So now let us look at this expression and then try to find out. We have done one result in earlier classes also, which mentioned limit of e to the power x minus 1 upon x when x tends to 0. So our idea is now to find out limit of this expression. How do we do that? See here, in this expansion, let us shift 1 to the left hand side. So on the left hand side, we have e to the power x minus 1. Now in all these terms, let us take x common. So we have from the first term 1 plus from here x upon 2 factorial, next term x square upon 3 factorial, and this term would be x to the power n minus 1 upon n factorial, and so on. Okay, now bring this x to the left hand side. So we have x minus 1 upon x, which is equal to this expression. Now in the next step, let's take the limit. So I'm writing down here only, limit x tends to 0 of this expression would be equal to limit of the expression on the right hand side. Now by direct substitution, the moment you put x is equal to 0, all these terms would convert to 0. What is left is 1. So on the right side we get 1. Hence we get to know that limit of the exponential function minus 1 upon x is, when x tends to 0, is 1. This is an important result which we have used, or we may even use in future. What is important in this result? You have to understand that here the power of x, the power of e, is same as the denominator. That means if the power is, say, x minus 2, then here also the denominator should be x minus 2. The power and the denominator is same, and the limiting point is not 0. Limiting point is that point where the numerator and denominator acquire the 0 form. So when is this possible? When x is 2. So x is 2, denominator is 0. X is 2, numerator also becomes 0. In that case, the standard result says the limit of this function is 1. So if you remember the basic standard result, we can easily obtain other important results. Now looking at this expression only, let us find out derivative of the function. So left side derivative, and on the right side, when you differentiate these terms, you know the first term derivative is 0, next term derivative is 1. Moving on to the next term, it is 2x upon 2 factorial, which I'll write as 2. Next term derivative 3x square, and the denominator 6, and so on. So if you have a closer look here, it is 1 plus 2 gets cancelled, next term is x. Over here this gets cancelled, you can write it down as x square upon 2, and on a similar basis we know the next term would be x cube upon 3 factorial. 2 can be written as 2 factorial, here is 1 which can be written as 1 factorial, and there are more terms. And on careful observation we note that we get back the exponential series. So derivative of e to the power x is the function itself. If it is not x, then it is a composite function. So whenever we differentiate exponential function, of course we'll get back the exponential function, and then differentiate 2x, you get 2. This is a derivative. If it is e to the power sine x, the moment you differentiate, you get back the exponential function, right? And then differentiate the power, which is cos x. So using chain rule, this is how the derivative is obtained. So this way we have discussed the exponential function in details. Now in the next class, we shall be studying about the inverse of the exponential function.